Yeah, your critics are. No, we can't see her.
Your eyes will adjust in just a second. Give it a minute. Shh. Connor, do you have a pass? You should have one. Can you stop by the office and grab one real quick? Thank you. All right. So we just finished talking about polynomials. We're going to kind of continue the pattern for this course, and we've kind of closed talking about one type of function. So we're going to start talking about a new type of function. In this chapter, we're going to be talking about radical functions. And when we say a radical, what we mean are things like square roots or cube roots or fourth roots. In general, we would call these guys nth roots. So this number here that's like in the little check mark, this is called the index for the radical. So notice for the square root, we didn't write in an index number, right? What number is there that we choose not to write? A 2, like square root. So we have to remember that there is an index of 2 there, even though we don't write it. That'll become important a little bit later on in the chapter, that we remember that, just like we have to remember like there's an exponent of 1 that we don't write, or a coefficient of 1 that we don't write, but not an unfamiliar move there, right, in mathematics, where we just stop writing the symbol that goes in a spot, because if there's no symbol, we just understand it to be this very common situation. The piece that's underneath this radical, this has a name. Thank you, sir. This is called the radicand. So whatever the number underneath the root is called the radicand. Okay. So that's just a little bit of vocab. Everybody's okay with that vocabulary? Nothing crazy there. So let's think about what the definition here is for, say, a square root. So let's say the square root of a is equal to x. What does that imply to us? That x squared is equal to a. So for example, if we have the square root of 9 is equal to 3, that tells us then that 3 squared is 9, right? Y squared well, it should be matching the index on my radical. So if we have then the cube root of a is equal to x, what does that imply to us then? X cubed is equal to a. So for example, the cube root of 8 is 2. So 2 cubed should give us 8. Is everybody okay there? And so if we extend this then to the most general situation, if I have that the nth root of a is equal to x, what does that tell us? That x to the n should equal a. And this is kind of, when we talk about the definition for a radical, this is kind of how we would define it in the most general way possible, where n could be any of these positive whole numbers greater than 2. Is everybody okay with that idea? Okay. Now, can we always take like the square root of a number? No, right? What kinds of numbers do we have issues with? Negatives. So this is something we spent some time talking about, right? And why is that the case? Yeah. It's not a real number, though. Those are, we needed to use the imaginary numbers to deal with that, right? And we know that this is an issue because if I try to apply my definition, there's nothing that we can square that can give us a negative number, right? So if I multiply a number to itself, it has to give me a positive. If both numbers were positive, you get a positive. Both numbers are negative, you get a positive. And if it's, if you're multiplying a number to itself, it's the same number, so you can't have positive and negative kind of thing going on, right? Is everybody okay with that idea? Does this extend to all radicals? Well, let's just take one step forward. Let's ask, what about the cube root of -1? Can we do that? Well, if that has an answer, there should be something that I can raise to the third power to get -1. Everybody agree with that? Is that possible? It is. What would that number be? It's -1. Because -1 times -1 times -1 is -1, right? -1 times -1 is +1. And then +1 times -1 is -1. So we see that some radicals we can take like the cube root of a negative, but we can't take the square root of a negative. So sometimes this is going to work and sometimes it's not. Do you suppose there's a way to predict when we'll be able to take the radical of a negative? What do you guys think? Is it going to be predictable? It'd be a pretty crummy situation if it wasn't, right? So when do you suppose we're going to be able to take the radical of a negative? So in general, if I take the nth root of negative 1, is defined for which n's? So that's what we're curious for, right? When can we take the radical of a negative? What types of radicals? Well, we know n equals 3 works, right? We just established that. Is there another one? 5? 7 will work. 9. We get the idea here. What are these numbers? Positive, odd numbers greater than or equal to 3, right? So 3, 5, 7, 11, 13, 15, 17. All of the odd roots we can take on a negative. Let's just demonstrate why real quick here with the 5th root. If I take negative 1 to the 5th, that's the same thing as this. And when I multiply these pairs of negative 1s together, I get positive 1s, but I still have one left over negative, right? So that's going to work. I can get negative 1 by taking some number to the 5th. Everybody's okay with that idea? So then let's worry about when it's undefined. So what values of n is can we not take the radical of? The even starting with 2. Exactly right. So these are just the positive even numbers greater than or equal to 2. So you can't take the square root of a negative, you can't take the 4th root of a negative, the 6th root of a negative, the 8th root of a negative, etc. are all going to be issues for us. Is everybody okay with that idea? Okay. So we should have at least a bit of an understanding of like what are the different kinds of radicals, right? When you can take the radical of a number and when you can't. You can always take the radical of a positive. You can always take the radical of a 0. If you're taking the radical of a negative, that's going to work if it's an odd root, and it would not work if it's an even root. Everybody's okay with that idea? Good. So we have enough now to start talking about graphing. Square root and cube root functions. And that's going to be the focus of the lesson here today. This is what you're going to have to do in the homework, is to do some of these graphs. So for the general square root function, we have this and our general cube root function. We have this. Notice I've used these familiar A, H, and K coefficients in here. Do you guys remember what the A, H, and K's do in terms of transforming the parent function? So let's focus on the A first. So A does two things. What are the two things, the two types of transformations A are responsible for? So you have a reflection. So when those A's are negative, you have a reflection across the x-axis. So they're in charge of the reflections. What else do they do? They do not reflect across the y. They're also in charge of the dilations, so the stretching. Do you remember what the H's do? What type of transformation the H's do? Not up and down, but they are in charge of a translation. Yeah, they are in charge of moving things left and right. And that means, what do the K's do then? No, they're the up and down. So they're also translations. They're just the other dimension translation. So this is all things that we saw in first semester. It's the same list that we've written down, I don't know, 2 or 3 times already. I think at one point I asked you to memorize these. I can see that we did a good job with that. So, for example, maybe we have the square root function y equals -2 times the square root of x plus 5 minus 1. What are our values for A, H, and K? A is -2. What is H? -5. And K is -1. Remember, the h's are always the opposite sign of what it appears in the function. Okay. So because a is -2, what does that do to our graph? Well, since a is negative, we're going to have a reflection across the x-axis. And because the absolute value of a is greater than 1, we're going to have a vertical stretch. So two things happen there from a. Is everybody okay with that? What is the h going to do? Yeah, since the h is negative, we're going to go left 5 units. And how about the k? Good. So that's going to go down because the k is negative. And it'll go down 1 unit. We kind of remember doing this. We did this when we talked about absolute value functions quite a bit, right? Or even like the vertex form quadratic function, right? We could do the same, had the same discussion. Okay. So when we talk about graphing these square root and cube root functions, I'm going to ask you to find points that are not irrational. So remind us again, what does irrational mean? Yeah, it's a decimal that can't be written as a fraction. And an example of that would be things like the square root of 2 or the square root of 3, but not the square root of 4. Why not? Because the square root of 4 is just 2. Yeah. Everybody okay with that idea? So we're going to have to be pretty careful about picking our x's. So for square roots, what's our smallest perfect square? What's the smallest number that we can take the square root of and get an even number back? There's a number smaller than 1. 0, right? Okay, what's the next number like that? 1. Okay, and then 4, and then 9, and then 16. So these numbers are going to be very important to us when graphing our square root function, because we want whatever's underneath that square root symbol to eventually turn out to be these 5 numbers. So for cube roots, is there a smallest number we can take the cube root of? Others number smaller than 0. Because remember, we can take the cube root of negatives. So is there a smallest?
Like smallest is not close to 0, or smallest is like bigger than negative.
So smallest is smallest. So negatives are smaller than 0. There's smaller than -1.
Negative is 100, that would be like.
That would be, there's one smaller than that. Although that's not a perfect cube.
Infinity.
There is not a smallest one, right? So we're going to have to come up with a slightly different, you're right, it is infinite. We're going to have to come up with a slightly different tactic. So rather than starting with the smallest perfect cube, what we want are we're going to find 5 perfect cubes that are closest to 0, because 0 is one of the perfect cubes. So what's the next perfect cube after 0 and the first perfect cube before 0? You've said it already. -1 is the first perfect cube before 0, and the first one after 0 then is +1. Okay. What's the next perfect cube after 1 and before -1? There's one before 27, although that is a perfect cube. So 27 is 3 cubed. 1 is 1 cubed. What are we missing? 2 cubed, or 8. And then also -8. So when graphing graphing a cube root function, these 5 numbers are going to be very important to us. Everybody okay with that idea? So for the function y equals a times x minus h plus k, I want that first number, when I plug in my value for x, to give me 0 underneath the square root. Everybody okay with that idea? Because that was our first perfect square. Notice underneath the square root, I have x minus h. So what value would I pick for 8 or for x? Well, I just pick 0 plus h. If I plug in 0 plus h, the minus h is going to cancel out with the plus h, and I'm going to be left with just the square root of 0. Everybody okay with that idea? And then similarly, so when I plug in x plus h in for x, the plus h and minus h are going to cancel out, and leaving me with a number that I can take the square root of and get an even, like a whole number back. That's why. Does that make sense? Okay. So 0 plus h is really just what? Just h, right? And then we can find the y coordinates. You could plug in the values for x, or you can just use this shortcut. what are these numbers 0, 1, 2, 3, and 4 coming from? Yeah, it's the square root of 1. It's the square root of, or square root of 0, square root of 1, square root of 4, square root of 9, and square root of 16. And again, just FYI, a times 0 plus k is really just what? Just k. So let's look at an example. Let's say we want to graph y equals -1 times the square root of x plus 2 minus 3. So I'm going to start by writing down my values for a, h, and k. What's my value for a? -1. What's my value for h? -2. Remember, the h is always the opposite of sign of whatever it appears in the function. And k is -3. So now I'm going to make my xy table. And I'm going to use my formulas that we just developed directly above to fill in. So I'm going to have 0 plus h, 1 plus h, 4 plus h, 9 plus h, 16 plus h. Then I'm going to have a times 0 plus k, and then a times 1 plus k, a times 2 plus k, a times 3 plus k, and then a times 4 plus k. Is everybody okay with how I filled things in there? So now I'm just going to go ahead and do these little operations here. So I'll begin by plotting -2, -3, and then -1, -4, and then +2 and -5, and then 7, -6, and then 14, -7. Oops. So how am I going to connect these points? Well, I guess my question is, when I draw my graph, should my arrows be going one way or both ways? Just one way. Which direction should the arrow be pointing? To the left or to the right? Has to be to the right. Why is it going only one way? Because can you take the square roots of negatives? No, if I put in a number less than -2 up here, what's going to happen underneath my radical? Like if I plugged in -3 for x, what's going to happen? Look up here. If I put in -3 for x, what do I get? I get a negative number, and I can't square root that. Everybody's okay there? So I need to make sure that that arrow is only going one direction. And when I look at your guys' graphs on a test or a quiz or whatever, I'm going to be very, very picky about what I'm seeing right here. If I see something like this, I'm marking that wrong. So you must not have any part of your graph before that first point. Everybody's all clear on that? So notice, see that little tail hanging off the end of that? That's wrong, and I would mark off for that. Needs to look like this. Okay, so you have to, I'm going to be picky about that, and I need you to be quite careful. Okay? I want to talk about one more thing with regard to square root graphs, and that's domain and range. The domain is quite easy, so it's always going to be h to positive infinity. The range has two situations. So if that leading coefficient, that value for a is positive, our range is k to positive infinity. And if that leading coefficient is negative, we're negative infinity up to k. Is everybody okay with this? So for our graph up here, what's our domain going to be? Great. What was our h again? -2. And we got to have a bracket on the -2 and a parenthesis on the infinity. Because remember, what does the bracket mean versus the parenthesis? Bracket is included. The parenthesis is not. Notice at that point where we have the x-coordinate -2 is a real point on our graph. So the -2 needs to be included. What's our range going to be for this graph that we just drew? Very good. Feel okay here? Let's talk about cube root graphs then. So we're going to pick our x and y's very similarly to what we did before, but because we're talking about a cube root, the 5 numbers that we're going to add h to are different. These 5 numbers were the 5 perfect cubes that we found before, -8, -1, 0, 1, and 8. And then as a result, our numbers here will be different. And again, just like before, I'll point out that 0 plus h is really just h, and 0 times a plus k is really just k. So let's do an example. So let's say we want to graph y equals 2 times the cube root of x minus 1 minus 3. What's my value for a? 2. What's my value for h? Positive 1. And what's my value for k? Negative 3. So I'm going to make my xy table now using that little formulas that I have above. So I have negative 8 plus 1, and then negative 1 plus 1, 0 plus 1, 1 plus 1, and 8 plus 1. Then I have negative 2 times 2 plus negative 3, negative 1 times 2 plus negative 3, 0 times 2 plus negative 3. And then I have positive 1 times 2 plus negative 3, and then positive 2 times 2 plus negative 3. So now if I just evaluate these little problems here that we've made. Oops. We get these. Everybody okay with that? So now we'll just plot these points. Let's see, 1, 2, 3, 4, 5, 6, negative 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 1, 2, 3, 4, 5, 6, 7. So I'll start by plotting negative 7, negative 7. And then I'll have 0, negative 5. And I have 1, negative 3. And then 2, negative 1. And then 9, positive 1. Everybody okay here? All right. So when I draw this graph, am I going to need arrows at one end or both ends? Both ends. Why both ends here? Exactly, because we can take cube roots of positives and negatives. So I need arrows at both ends. Okay. And again, when you're graphing this, I'm going to be picky. I'm going to need to see arrows at both ends of your graph for the cube root ones. Okay. One last thing to talk about here for cube roots, and that's domain and range. This, though, are easy. Notice if we look at our graph, and we're talking about the domain, do I have an arrow pointing to the left? Do I have an arrow pointing to the right? Is the line connected in between them? So what's the domain gotta be? Yeah, all real numbers, so negative infinity to positive infinity. Now let's talk about the range. Do I have an arrow pointing down? This arrow's angling down. Doesn't look like it because I drew a bad picture. Do I have an arrow pointing up? Yep. And is it connected in between? So what's that tell me about the range? Same thing also. So the domain and range for cube root functions should be very easy. It's always going to be negative infinity to positive infinity for each. Any questions about what we've done here today? Good.